All right, in this lecture, we'll talk about radioactivity. So radioactivity is the emission of a tiny, indivisible particle from the nuclei of certain atoms. So if an atom emits these particles, it's called radioactive. So here's a depiction of that. So here we have this atom and this nucleus, and the nucleus emits some particle, and that's radioactivity. So not every atom is radioactive. In order for something to be radioactive, generally it needs to have an unstable nucleus, and this generally has to do with the ratio of protons to neutrons, and that's different for different atoms. But it undergoes this radioactive decay because it has this unstable nucleus. It wants to be stable, and it wants to be at lower energy. And so we go from this high energy unstable nucleus to this lower energy more stable nucleus through radioactive decay. Let's just review isotopes, and this is important for a couple of reasons. One, because isotopes or different isotopes of different elements may or may not be radioactive. So you could have like some isotopes of uranium might be radioactive and the other ones aren't. And also because when we write out nuclear equations, we are going to write them out with this notation because we're talking about taking some atom and changing the number of protons or the number of neutrons or both. And so we want to depict that in our chemical or nuclear equation. So again, when we talk about isotopes, just to refresh your memory, we use this AZX notation where A is the mass number, and remember the mass number is the number of protons plus the number of neutrons. C is the atomic number, and remember the atomic number is the number of protons. So every element or every atom of a particular element will have the same atomic number because the number of protons defines that element. But not every atom of an element will have the same mass number because they can have a different number of neutrons, and that's what makes them different isotopes. And then X is the chemical symbol. So here we look at two different isotopes of neon. See, they both have the same atomic number of 10, which they should. They both have 10 protons because for an element to be neon, it has to have 10 protons. And then here we have neon 21, which means this has 11 neutrons because remember the mass number minus the atomic number gives you the number of neutrons. Here we have neon 20, has 10 neutrons, again 20 minus 10 is 10. And here's some subatomic particle notation. So we also will write subatomic particles in the same type of notation when we're writing these nuclear equations. So for a proton, we have this P11, which makes sense, right? It has an atomic number of 1 because that's the number of protons, just 1, and then it has no neutrons, it's just protons, so this should be the same 1. For a neutron, it should have an atomic number of 0, because remember that's the number of number of protons, and then it should have a mass number of 1 because this is the number of neutrons plus the number of protons. And then finally for an electron, it has a mass number of 0. Remember, it has no neutrons and no protons, so it's 0. And then we put down here -1 because of the charge. Okay, so now we're going to talk about different types of radiation. So the first type we'll talk about is alpha radiation. So alpha radiation occurs when an unstable nucleus emits a small particle that consists of 2 protons and 2 neutrons. So here's just kind of a depiction of an alpha particle. So this particle is identical to helium-4 nucleus. So when we write out nuclear equations, we'll put in helium-4 and just know that that is what an alpha particle is. So in alpha decay, you'll have here's the radioactive atom. It undergoes alpha decay, emits an alpha particle, or helium-4, which again is 2 protons and 2 neutrons, and then we have this atom that comes out of it. So what we call the radioactive atom is the parent nuclide, or just the parent atom. So that's the radioactive element. The daughter nuclide, or the daughter atom, is what atom comes out after it undergoes decay, whatever type of decay it undergoes, and then we have this alpha particle, or whatever particle is emitted. So again, parent atom is the radioactive atom, and daughter atom is the one that comes out after the parent atom undergoes decay. So for nuclear equations, we write them out like this. So let's go through that. So here we have uranium-238. It undergoes alpha decay, and I know it's alpha decay because it emits this helium-4 to make thorium-234. So when you have these nuclear equations, the sum of the atomic numbers and the mass numbers on both sides of the equation must be equal, because we can't gain or lose protons or neutrons. They have to all still be there, right? So just like when we're talking about balancing regular chemical equations. So here we have the parent atom, here are the daughter atoms. So here we have 238 for mass number, and here we have 234 plus 4, so that's 238. It's the same. And then here we have this atomic number of 92. Here we have 90 and 2, so that equals 92, so we're good. So when you're looking at this nuclear equation, and when we're talking about nuclear equations, there's a couple things you need to look at. So you'll look at your parent atom, and then your daughter atoms, and then, right, like I just said, you need to make sure the sum of the atomic numbers and mass numbers are equal on both sides. And then you can tell what type of decay you have, because you'll look at what particle is emitted. So here we have an alpha particle, so this is alpha decay. And we know what atom the uranium decays to, because since we know we start at atomic number of 90, and we know we emit this helium-4, which has an atomic number of 2, we know that the other element has to have an atomic number of 90. And so you can just go to the periodic table and look up, okay, what element has the atomic number of 90? And then it's thorium, and then you can put that in. So that's how we write nuclear equations. So there's different nuclear equations for each type of decay, and at the end I have kind of a summary chart that shows you the different nuclear equations for different types of decay. So some properties of alpha radiation. So alpha particles are the largest particles emitted by radioactive atoms. So they have the most potential to damage other molecules, including biological ones. And this is called ionizing power. So they're really damaging, but since they're so big, they can't penetrate matter very easily. So they have the lowest penetrating power, which is the ability to penetrate matter, and this has to do with its size. And so a piece of paper or clothing can actually stop an alpha particle. It can't go through a piece of paper. So that's good, because since these are so damaging to biological molecules, it's easy to block them. But they are very damaging, so you don't want to be around them without some kind of protection, right? So the next type of radiation we'll talk about is beta radiation. So this occurs when an unstable nucleus emits an electron. So you're thinking, okay, well, a nucleus has protons and neutrons, no electrons, so how can a nucleus emit an electron? Well, actually what ends up happening, this electron results from the conversion of a neutron to a proton. So you have your daughter element, or your parent atom, which I'll show you this in the next slide, and then one of its neutrons turns into a proton, and then an electron gets kicked out. So the proton is still in the nucleus, just the atom leaves. So beta particles have intermediate ionizing power and penetrating power. So here's a depiction. So like I said, so here we have this carbon-14 nucleus. Here's a neutron. It undergoes beta decay. So this neutron changes to a proton. So an electron has to come out. So we go from carbon-14 to nitrogen-14. So since we gain a proton, our atomic number has to go up by 1, right? The next one is gamma radiation. So gamma radiation doesn't emit matter, but it is actually electromagnetic radiation. So gamma rays are really high energy photons. They don't have a charge or mass, and they're usually emitted in conjunction with other types of radiation. Gamma rays have low ionizing power but high penetrating power, so they can get through just about everything. And then finally, positron emission. Positron emission occurs when an unstable nucleus emits a positron, and a positron has the mass of an electron, but it's a positive charge. So this is the opposite of beta radiation or beta decay. Here, remember in that, a neutron changed to proton, so we emit an electron. Here, in positron emission, a proton changes into a neutron and emits a positron. So here's a picture of that. Here we have our nucleus of our positron emitter, we have a proton, it turns to a neutron, and emits a positron, which is the same. We write this the same as we write the electron, but instead of -1, it's +1 down here. Just the charge is different. So here's a summary. So the 4 different types of decay that you need to know about. So let's just review really quick. So alpha decay, remember, parent atom goes to a daughter atom and emits an alpha particle, which is helium-4. This has high ionizing power, which means it's very damaging to biological molecules and other molecules, but it has low penetrating power. Remember, it can't even get through a piece of paper. And then here's an example. So we have uranium going to thorium, emitting an alpha particle. Then beta radiation, remember, is when a neutron becomes a proton and emits an electron, and it has moderate ionizing power and penetrating power. So here's an example of that. Gamma radiation is when an excited atom goes to a stable atom and it emits some photon or this gamma particle. And here's an example of that. So thorium-234 going to thorium-234, but it emits this gamma radiation. It has low ionizing power but high penetrating power. Then finally, positron emission, remember, is the opposite of beta emission or beta decay. You have this parent atom, one of its protons changes to a neutron and emits a positron, which is, remember, the same mass as an electron, just opposite charge, and it has moderate ionizing and penetrating power, just like beta decay. And then here's an example of that. Here we have phosphorus-30 going to silicon-30 and emitting a positron. So when you're looking at nuclear equations, what you want to look at is what's my particle emitted, and that will tell you what type of decay you have. So if I see this helium-4, that's an alpha particle, I know I have alpha decay. If I see this electron emitted, I know I have beta decay. If I see this gamma particle emitted, I know I have gamma decay. And finally, if I see this positron emitted, I know I have positron emission. And that's how you can tell by looking at the nuclear equations. And then you do need to know about ionizing power, penetrating power, exactly what happens. So for example, beta decay, you need to know that a neutron turns into a proton, and that's why it emits electrons, so on and so forth. So this chart kind of has everything you need to know in it. So particles emitted from radioactive nuclei contain a large amount of energy, and so they're really easy to detect. And so radiation detectors detect the particles through their interactions with atoms or molecules. So you'll have some detector, and they all work differently. And they, well, if you have an alpha particle or a beta particle or a gamma ray come through the detector, it'll react with something in the detector, and that's how you know that you have radiation nearby. Finally, we'll just briefly talk about half-life. So different radioactive isotopes decay at different rates. So a sample that decays quickly has a short half-life, and a sample that decays slowly has a long half-life. And half-life is the time it takes for half the parent nuclides in a radioactive sample to decay to their daughter nuclides, and so that's how we define it. And it's exponential decay. It's not linear decay. And we can actually take advantage of known half-lives to date objects, and that's how we do carbon dating. So we know, carbon-14 has this half-life. So if we measure how much carbon-14 we see in a sample, we can calculate backwards to figure out how old it is. And here's a picture of this. So the half-life of thorium-232 is 14 billion years. That's really slow. So that means if I have a sample, and here, for example, we have 1 million atoms. It's going to take 14 billion years, I apologize, to have 500,000 atoms. And then in another half-life, we'll have half of that. In another half-life, we'll have half of the previous one, so on and so forth. So you should kind of understand how this works. And if I give you, let's say I tell you this, you have this thorium-232 sample, you have 1 million atoms, its half-life is 14 billion years. How many atoms will you have after 2 half-lives? And just remember, it's not, what you have to do when you do each one is you go from one half-life to the next half-life to the next, because this is half of this, 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 so on and so forth.